we are going to do today is we are going to work with pH, all right? And pH is something you've heard about and you've learned about since primary school. You hear about pH, and when we, for instance, measure the pH of the swimming pool, your mom or your dad or even yourself at home may get a little testing kit. You buy it at the pool shops, and then you go and then you take some water out of your swimming pool, and then you put some chemicals in it, which are basically indicators, and then you check to see what the color is, and it tells you what the pH is, and based on the pH, you add certain chemicals. Okay, now, but what is pH? What does pH actually mean? Does anyone know why it's pH? Potential hydrogen. That's what the pH stands for, okay? Potential hydrogen. So we are going to look at how we can work with pH quantitatively, in other words, mathematically, all right? So firstly, let's first look at measuring the acidity of an acid, okay? So the acidity of an acid is measured in concentration of hydrogen ions, okay? Measuring the acidity of an acid. So I'm going to state here that the acidity is dependent on the concentration of hydrogen ions in a solution, right? So the higher the concentration of hydrogen ions in solution, the higher the acidity. It is not a direct dependency. This is not direct proportionality, okay? So we have learned in earlier workshops, we've learned that if you have an acid, let's take for instance, you have HCl, right? And you react it with water, then you're going to get a hydrogen ion or a proton that is going to be donated. In the case of hydrochloric acid, it's a strong acid, right? So the ionization process is going to be very, very dominant. The recombination is tiny, all right? We're going to land up with a chloride ion, and we're going to land up with a hydronium ion. A hydronium ion, okay? Now, we've worked with conjugate acid bases. We've worked with the Bronsted-Lowry. The Bronsted-Lowry says that an acid is a proton donor. So this would be the acid. The water would be the proton acceptor. So the water would be the base. So pair 1, this would be the acid. And this would be conjugate base 1. Right, and with the water, that would be the proton acceptor, and we learned there that this would be pair 2, and so this would be a conjugate acid. We've learned this. Now, the thing is this, is the stronger the acid is, the more hydronium ions it's going to produce in solution, okay? The more concentrated your acid solution is, the more hydronium ions you're going to have in solution. So we can actually, and I prefer to do this, and I'm the first one to admit that I'm not a specialist chemist. I'm not a chemist, okay? But I think as a school teacher, that's sometimes an advantage because I have struggled with this as much as what you probably struggle with it. So I sort of go, okay, what was the easiest way for me to understand this? So I prefer, rather than refer to it as the amount of hydrogen ions in solution, I like to refer to the amount of hydronium ions. Either of them is fine. It doesn't matter. Okay. Now, we use indicators. Have you done indicators in your classes as of yet?
What is the
Proportionality. Dependent on.
So what is the difference between proportional and direct?
Okay, proportional is a stronger statement where it's inverse or direct proportionality. This you can see as more as dependency on. It is not a direct dependency because it's logarithmic.
So you mentioned the stronger an acid.
The stronger an acid, the more it's going to ionize, the higher the concentration of hydronium ions. Also, the more concentrated it is, the more hydronium ions you're going to have in solution. All right. Now, today I am not going to focus on indicators. That is not the purpose of this workshop. But an indicator is a substance which displays a specific color depending on the concentration of the hydronium or hydroxide ions in solution. So pH can be determined to a certain extent by indicators. Now, if you are colorblind like I am, indicators are not very useful, all right? Because I have a bit of a problem with color discrimination. So I can see primary colors, blue, red, green, that's fine. But when it starts to get these shades, and then I go like, okay, well, I can't see that this is pH 7.5 or 8.9 or 3.5, whatever. So then you use, today we have what we call digital pH meters, and they give you a value for the pH. All right, so my focus today is going to be on pH and pH calculations. Have you done indicators in your classes? Did you do it today? Okay. All right. I will still make a video on indicators because indicators are actually weak organic bases, right? And you use Le Chatelier's, but you haven't done Le Chatelier's yet. You actually need to have done chemical equilibrium in order to understand how indicators work. All right, but I will still do a video lesson on that. All right, now, if you use universal indicator, which is a mixture of organic indicators, then you get a range from pH 1 to pH 14. Now, strong acids have got low pHs. You are taught this from primary school, but you're not taught why. You're not taught why. Because if you're down here, you have actually got acids that are producing large amounts of hydronium ions. So the concentration of hydronium ions or hydrogen ions is high. So why is the pH low? Kind of doesn't make sense. And if your hydronium ion concentration is low, why is your pH high? Okay, you'll soon enough see why. So we are now going to look at what is pH, all right? So pH is the abbreviation for power of hydrogen or potential hydrogen. So a definition of pH is a quantitative measure of the acidity or alkalinity of a solution. I'm going to say it again. A definition of pH is a quantitative measure of the acidity or alkalinity of a solution. By quantitative, I mean that you can actually associate a number to it. Right, now, the formula that we use for pH is this formula here. pH is equal to the negative of the logarithm of the hydronium ion concentration. Now, you are grade 11s. This is usually done in grade 12, when you have already done logarithms in mathematics. Who of you have actually done logarithms in mathematics? None of you. Okay, all right. So there's an advantage and there's a disadvantage. The disadvantage is that you haven't done it. The advantage is I'm actually a mathematics teacher in disguise. Okay. I've taught this for many years, so I think I can give you an insight into logarithms enough in order for you to be able to use it with relative confidence, okay, in your exams. So now let's go to a logarithm and let's see what does this mean. Okay, so I'm going to not digress. I'm going to take about 10 minutes to talk about logarithms. So let's go. So what is a logarithm? What is a logarithm? Okay. Logarithms are strange things, okay? But they're exceptionally powerful. So let's look at an example. If I've got a number and it is equal to a power of a base b to an exponent x. So this could be, for instance, 10,000 equals 10 to the power. 10,000 is 10 to the power 4. That's your logarithm. 4 is the logarithm. Okay, I'll go, well, Mr. D, that still doesn't make sense. Okay, so let me show you. If n equals b to the x, we call this the exponential form. Right? So 10,000 can be written in a power, yes?
So now, please quickly run again.
Yeah, sure, you can go. You can go. So 10,000 is 10 to the power 4. So that's the exponential form. All right, so now if I take this and I say the following, if n equals b to the x, then here it goes. The logarithm of n to the base b equals x. I'm going to write out how you say it. Language is very important, okay? The way you say it is the following. The logarithm of n to the base b is x. All right. Now, this form here is known as the logarithmic form. And this is the definition of the logarithm. All right. Now, the way I understand it is in the current mathematics syllabus, they have reduced the amount of content on logarithms. So you mainly use it in the context of logarithmic graphs. Okay, I have no control over the mathematics syllabus. In days gone by, when Noah and myself did mathematics 40 years ago, we actually had logarithmic tables instead of calculators. Right. Yeah. Have you ever heard of a slide rule? There was another form of calculator using logarithmic scales. So logarithms were used before calculators. Yeah, that's how old I am. Okay. The first time I got a calculator, I think, was when I went to university. At school, we had logbooks. We even used the logbooks for trigonometry. Okay. Yeah, that's a long time ago. All right, so let me rewrite this. I would like to write the definition as follows. Right? Less haste, more speed. The quicker, the more we spend on logarithms, the easier the calculations are going to be. So the definition is, if you have n equals b to the power x, that implies that the logarithm of n to the base b is equal to x. So here we go from a logarithmic to an exponential, from an exponential to a logarithmic form. Yes.
So what I don't understand is what do you mean by to the base b?
Isn't this power to the base b?
Oh yes, but why is the b going next to the log?
Because that's the notation of
Is it
logarithm.
like a sub?
Notice what I'm saying. The logarithm of n to the base b equals x.
So is it like
Can I ask you to just wait and let me do a few concrete examples and you will answer your own question? Okay, I've been doing this for a long time, okay? I know what you're asking, but I know also how it's going to be answered. Okay, so it's also true in reverse. And this is what we are going to use extensively in pH calculations. We are going to use this a lot, and this is why it's important for you to be aware of this. So let's use an example. Let's start simple. 100 is the number. If I'm going to make that number a power of 10, in other words, I want to make a power of 10. The base is going to be 10. Okay. The logarithm is the exponent to which I raise 10 in order to get the number. What's that value? 10 to the 10, it's 2. It's 2. So another way of writing this is to say, well, we know that's true, so let's say it. I had the privilege of meeting a professor of mathematics in the US. And him and his wife, she's a physicist and he's a mathematician, he's a professor. And he and her have spent decades studying the importance of language in mastering concepts. And with logarithms, it's important that you say it, not just write it. So 100 equals 10 to the 2 implies that the logarithm or the log of 100 to the base 10 equals 2. Okay, now you might be saying, my goodness gracious me, why on earth would we complicate our lives by writing something that is so simple in such a complex way? And there's a very, very important reason why. The log rules are cruel. They take multiplication and change it into addition. They take division and change it into subtraction. They take raising a power and change it to multiplication. You will see this. But unfortunately, in our current math syllabus, I gather you don't do much on log rules in mathematics. So, and I'm going to show you this because you need it for POH plus pH equals 40. Okay. So, let us try something else. I want 1 billion to the power of 10. And I want you to write it as the logarithm of 1 billion, okay, equals okay. I'm using a color convention, so just to help you with that. So don't shout it out, don't steal anyone else's learning. What does this need to be? And what is this? Just give it a go. Anyone want to give it a go? No? You see, the logarithm of 1 billion to the base 10 is 9 because 1 billion is 10 to the 9. Okay, let's do another one. Take 64, let's do it this way. The logarithm of 64 to the base 2. What is this going to equal? Don't shut it out. My advice to you is convert this to that, and then you'll be able to find the answer. So go from logarithmic form to exponential form, and you'll get to see what the answer is pretty clearly. Tamu. 2 to the what gives you 64? 2 times 2 is? 4 times 2 is? 8 times 2 is? 16 times 2? 32 times 2? How many times did we multiply 2 by itself? 6 times. Isn't 2 to the 3 8? And 8 times 8 is 64. 2 to the 3 times 2 to the 3 is 2 to the?
6.
It's 6. The logarithm of 64 to the base 2 is 6. Now, I'm not going to spend a whole workshop on logarithms, but I've done enough in order for me to show you how we're going to use this with pH. Okay. Right. So, let's go to pH. So, with pH, we say that pH is equal to the negative logarithm of the hydronium ion. Now, we don't put a base in. And the reason why we don't put a base in is because this is called the common logarithm. The base is, as a standard, 10. So when we don't put the base in explicitly, it's base 10. So what this means is, right, let's look at an example, right? If I am told that the hydronium ion concentration in a solution is, for instance, let's make it 10 to the negative 4 mole per cubic decimeter cubed. Okay. By the way, your calculators help you with this. Okay. Your calculators can help you. We don't expect you to do this manually. All right. So we are told that the concentration in a particular solution is 10 to the negative 4 mole per cubic decimeter cubed. Let's say this is given to you. This is given to you. And we ask, what is the pH of the solution? Okay, then what we do is the following. We say, okay, pH is going to be the negative logarithm of the hydronium ion concentration, which is going to be 10 to the negative 4 mole per cubic decimeter cubed. Okay, I'm leaving the 10 out now. Let me put the 10 in for the time being. Okay, now, you can do this on your calculator, but I want you to see if you can try to do it without your calculator. So, follow with me. Follow the reasoning. Okay. Imran, all of you please take note here. Listen to the words. This is asking me the logarithm of 10 to the negative 4 to the base 10 is asking me, are you ready for it? What exponent must I raise 10 to in order to get 10 to the negative 4? Negative 4.
Is that it?
Let me say it again. What exponent must I raise 10 to get 10 to the negative 4? Negative 4. So this is negative 4, apologies. This is negative, this negative there, and the answer, this is just negative 4. And this gives us a pH of 4. which is less than 7, so it's acidic. Now let's do that with your calculator, all right? So it's not as difficult as it may seem. Now you might say, but why are we doing this? You're not always going to get your concentrations as nice as 10 to the negative 4.
Is the log 10 to the minus 4? You drew an arrow and this, what that arrow is for.
This
And
is negative 4. Let's take our calculators. All right. So let's take our calculators. I'm going to take a photo of my calculator. All right. I assume you have calculators that are similar. Okay. Okay. So what we're going to do, all right, we are going to say, all right, we're going to take the pH is the negative log of 10 to the negative 4. Now, in the exam, you're just going to use your calculator. You're not going to need to do it manually. So here's the key sequence. I am going to go to the negative. Please do it with me. I'm going to go to the negative. My key sequence is, first and foremost, I am going to press the negative button. Okay. Then I'm going to press the log button. Okay. Now there are 2 log buttons. There is a log and a ln. A log is to the base 10. Ln is to the base E, which is the natural base, for instance, in exponential decay and radioactive decay and that. Euler's number. You don't need to work with it. Okay? We are going to work with log base 10. If you go and you look there, can you see the inverse is 10 to the power? Right. So you're going to work with that log.
Sir,
Yes.
why is there another log to the top right?
Because this log enables you to work with any number to any base. We don't need it for logs, for pH. Okay.
So
Yes.
you can, like both of them, the logarithms up.
Don't need. Okay. Now, we are going to press the log. All right. Now, we got 10 to the negative 4. So if we look here, can you see that we can use that one or we can use that one? So I'm going to go and I'm going to say, right, if I look here, I'm going to go negative log. Okay. And I'm going to go, let's just see here. You're going to see I'm normally going to use this button here. I'm going to use this button. Normally we're going to use this button. All right, but for this one, I'm going to go, I don't normally use this a lot, but I think I'm going to press the 10 to the, yeah, that's it. So I'm going to press the 10. I'm going to go up here, shift to this. So I'm going to press shift. I don't know how good your calculator skills are. I think your calculator skills are normally quite good by this time. And we're going to press the 10 to the, all right. And what we're going to do is we're going to put in the negative 4. Okay, and that means we go back and we put in the negative. We put in 4, all right, to negative 4. Okay, and equals. And what does it give us? Answer is 4. Okay. All right. So you have the calculators in order to work this out. Okay. We're going to practice some more. We're going to practice some more. All right.
So, sir, if we were writing it out fully, would it be negative log and then 10 as the B? And then,
Sorry, if we were writing it as?
like if we were writing it in the form of the
exponential form.
the exponential.
Okay, we're going to get to the exponential form. I'm going to do that just now. But first, when we're going to do the reverse calculations. We're going to use that. So why it's a good question. We're going to come to that. So what I want us to do now is I want us to go and look at another example. Okay. Example, determine the pH of a solution of HCl which has a concentration of 0.018 mole per cubic decimeter cubed. Okay. We're now converging on the types of questions you could get in a test or an exam. All right. Now, do you remember those ionization equations I spoke about at the beginning of the workshops? Can I please ask you to write out the ionization equation of HCl reacting with water? This is key. This is key. You need the ionization equation for HCl. So we've got HCl plus water, and there's a very small recombination, so we can basically say it fully ionizes. We can assume full ionization. There's going to be a transfer of H plus. It's going to leave us with Cl minus plus H3O plus. Now, ladies and gentlemen, this particular step you're going to see is where very, very easily you can slip up. Okay. Now, this is a strong acid. We are only going to ask you to work out pH of strong acid and strong base solutions. We will not ask you to do the pH calculations of weak acids and weak bases because it falls outside of our syllabus into university level chemistry, because then you need to work with Ka and Kb values, equilibrium constant values for acids and bases, which is not in our syllabus. Okay, so you will only get strong acids and strong bases. And the reason is, with a strong acid, you can assume full ionization, and therefore you can work with the molar ratio of 1 mole of HCl to 1 mole of H2O produces 1 mole of chloride ions to 1 mole of hydronium ions, which means that the concentration of the hydronium ions will be the same as the concentration of the HCl solution. That is super important, because when it comes to diprotic acids like sulfuric acid, 1 mole of H2SO4 is going to produce 2 moles of hydronium ions. Okay, so now what was the concentration of HCl? Well, it was 0.018 mole per cubic decimeter cubed. So we can get the concentration of the hydronium ion from the concentration of the acid. Okay. Now, so the first step was the ionization equation, right? The second step was the molar ratio. The third step is that the pH is equal to the negative log of the hydronium ion concentration. Now, I would like you to take this value and with your calculators, please work out what the pH is. By the way, you're given this formula in your exam formula sheet. So use your calculator. pH equals the negative log of 0.018. And what does that give us?
Should we round to 3 decimal places?
We work with 3 decimal places. NSC works with 2 decimal places. We work with 3.
So are there any units?
No units. Very, very good question. pH doesn't have units. It's a logarithmic scale. By the way, there's another logarithmic scale that we know about, which we don't often realize it's logarithmic. The Richter scale. You know, for earthquakes?
Oh, yeah.
So when they tell you it was a 6 and a 7, it means the 7 was 10 times stronger than the 6 because it's a logarithmic scale. Okay. So now, if I do this, I go negative log of 0.018, I get 1,745. Tammin, thank you for asking that question. Okay, now what does this mean? What does this 1,745 mean? Can I show you what it means? If you go to the notes, right, your pH of 0 has got a 1 molarity. In other words, 1 mole per cubic decimeter cubed. If you go down 1, 2, 3, 4, 5, 6, 7, 8, when we get to 7, here we have a neutral solution. Neutral means the amount of hydroxide ions and the concentration of hydroxide and hydronium ions are equal and they neutralize each other. If we are here, this region here is a strong acid. This region here are weak acids. This region are weak bases, and these are strong bases. Okay. Now, remember earlier on I asked you, why does it switch around? Well, the reason why it switches around is because if you draw the log graph, this is how it looks. All right. So when you have a very low hydrogen ion concentration, in other words, it's basic, you have low pHs. Your pH is low. Sorry. Your pH is high. So when your acidity is low, your pH is high. When your acidity is high, your pH is low. It's got to do with the nature of the logarithmic function, which you will do in grade 12. So when your concentration of hydrogen ions is low, hydronium ions, and you're going to find your pH values are going to skyrocket. When your hydronium ion and hydrogen ion concentration is high, then your pH values are going to be low. We're not going to explicitly ask you about the graphs. Okay. So coming back to this means this is strongly acidic. You do not want to put your finger in the solution. Okay, so this implies strongly acidic. Okay, now I want to do the reverse. I want to give you the pH, and I want us to work out what is the concentration. And that's where we use what we call the anti-log, all right, which is switching to exponential form. Okay, so let's look at an example. Are you okay with this? Any questions until, okay? So let's look at another example, all right? So this example, determine the concentration of hydronium ions in a solution with pH 3.45. 3.45. Okay, now and why? This is where I'm going to answer your question. Okay. All right. So if we look at pH equals the negative log of the hydronium ion concentration to the base 10. It will always be to the base 10. The first, okay, and you don't need to do this the way I'm doing it now. Okay. You take the negative to the left-hand side by timesing by minus or by multiplying by minus 1. Okay. So this is going to be negative pH equals the logarithm of the hydronium ion concentration to the base 10. I'm going to change from logarithmic to exponential form. So this means that the hydronium ion concentration is going to equal the base 10 to the negative pH as the exponent. At this stage, before you've actually done logs in mathematics, you can use this. Now, this is very nice because 10 to the power sits above your log button, what we call the anti-log. Okay, so if I now go and I work this out, I can say, okay, so the hydronium ion concentration is equal to 10 to the negative 3,45, because my pH is 3,45. And therefore, my hydronium ion concentration is equal to, and now you just use your calculators. You say this is 10, this is 10 to the negative 3,45, and we get that this is a very small concentration, 3,548 times 10 to the negative 4, all right? And I'm going to use capital M for molarity. That's a symbol for mole per cubic decimeter cube. The reason why I've done that is I've run out of space here. Okay. Okay, now, one of the beautiful things about science is how, when you get certain concepts in place, how there's a domino effect of how other concepts just basically follow. Can you remember, do you remember the auto-ionization of water? Okay. Okay, let me remind you, and I'm hoping I can find it here pretty easily. I haven't got it, sorry, I haven't got the full. Okay, what I'm going to do is this. I'm going to go here, and I did this in a previous workshop. If we have water, H2O, and we have another H2O molecule, in a very unusual random event, they will collide with enough energy that one of the water molecules will donate its hydrogen ion, but it is very, doesn't happen often. So the ionization is beyond weak. In doing so, it produces a hydroxide ion, and it produces a hydronium ion in equal concentration. So therefore, it's going to be neutral. Okay, we're okay with that? Okay. So if we look here, this is known as the auto-ionization of water. All right, auto-ionization. The water, we know that water can be can be amphiprotic. It can behave as an acid and a base. In this case, this is acid 1 and this is base 1. Remember I said to you, weak acid produces a strong base. This is going to be a weak base 2 and it's going to produce a strong acid 2. Now we know that the hydroxide ion and the hydronium ion are like the purest form of acids. So the reverse reaction is going to dominate. Now, you haven't done chemical equilibrium yet, but next year when you do chemical equilibrium, you're going to learn about what's called the equilibrium constant. Now, this is something you're going to be given. Kw is the product of the hydronium ion concentration multiplied by the hydroxide ion concentration, and this equals 10 to the negative 14 at 25 degrees Celsius. All right, now I just want to make 100% sure of something.
So then what's your problem?
Sorry?
Yeah.
Yeah. So, yeah, I'm going to prove this to you, that this is on your formula sheet, right? And here's your formula sheet. I am going to show you where it is, right? This is the NSC formula sheet that you will get, right? (298) Kelvin is 25 degrees Celsius. 25 plus 273 gives you 298. All right, and there is your pH formula. Okay, so that you don't have to now remember it, you've got it. Okay, all right, so what I want to show you now, ladies and gentlemen, that this is the way you convert between concentration of hydronium ions and concentration of hydroxide ions. So if we go back to this question here, determine the hydronium ion concentration in a solution with pH equals 3.4. If this was the A part, let's say this was example, and this was the A part. Determine the hydronium ion concentration in a solution with pH equals 3.45. Well then, ladies and gentlemen, if I asked you then determine the hydroxide ion concentration in the solution or of the solution, then what you do is the following. You say the hydronium ion concentration multiplied by the hydroxide ion concentration gives us 10 to the negative 14 at 25 degrees Celsius, which we're going to assume is the temperature at which these solutions will be. Okay. Now, we have the hydronium ion concentration. We calculated from the pH. So now that we've used this, we can now substitute that in and say, well, okay, we've got 3,548 times 10 to the negative 4 moles per cubic decimeter cubed times the hydroxide concentration, which is unknown. This equals 10 to the negative 14. So therefore, if I divide both sides by this, I get that the hydroxide ion concentration is 10 to the negative 14 over 3,548 times 10 to the negative 4 mole per cubic decimeter cubed. All right. So now, 10 to the negative 14 divided by this. What does that give us? Well, 1 times 10 to the negative 14 divided by the answer gives that the hydroxide ion concentration is 2,818 times 10 to the negative 11 mole per cubic decimeter cubed. Now, I have a question that I would like to ask you. What do you notice about the relative sizes of the concentrations? When you compare this and this, what do you notice about this in comparison to that?
The hydroxide is bigger.
Oh, I mean smaller, sorry.
It's-
I thought it was negative 14.
No problem. It's fine. Remember, it's cool to make mistakes in science. It's fine. Can you see that this is way bigger than that by about 7 orders of magnitude? Ladies and gentlemen, it's because it's an acidic solution. There's way more hydronium ions than there are hydroxide ions because this is an acidic solution. Look at the pH. The pH was 3.45. It's a reasonably strong solution. Imran, are you okay?
Oh, yeah.
Yeah, okay. Now, I get so excited. Can I show you something? Okay. All right. So, now I'm going into my super nerd mode. Can you please tell me what is the pH of a neutral solution? 7, eh? Watch this. If I have a neutral solution, all right, would you agree with me that the concentration of the hydronium ion is equal to the hydronium ions is equal to the hydroxide ions? Would you agree with that? Okay. Now, if I've got that the hydronium ion concentration multiplied by the hydroxide ion concentration is 10 to the negative 14, and these two are equal, let's make this x. Then would you agree that this is x times x is 10 to the negative 14?
You just made up the 10 to the negative 14.
No, it's not. No, it's not 10. No, it's not made up. It's not made up at all.
It's something that.
It's called the ionization constant of water. No. It's not made up. It's not made up. It's the equilibrium constant of a acidic and basic solution. All right. This here will make more sense when you've done chemical equilibrium. This is the ionization constant for water at 25 degrees Celsius. This is an experimentally derived constant. Okay, now, if we now go back here, okay, by the way, there's in the notes, the auto-ionization of water. So I seem to have lost my space, okay. If these two are equal, then isn't this x squared? And if I square root this, isn't this the same as dividing the exponent by 2? But this is 10 to the negative 7. So therefore, the hydronium ion concentration is 10 to the negative 7. Therefore, the pH, which is equal to the negative logarithm of the hydronium ion concentration, which is 10 to the negative 7 to the base 10, well, what exponent must you raise 10 to get 10 to the negative 7? Negative 7. So this is going to be equal to negative 7. Hello, ladies and gentlemen. Your pH is 7. Oh, yeah! Yes! Can you see how it ties in? Yes.
But still, how would they? I just don't understand how they would figure that out themselves. Like about
Okay.
the pH.
You've got very clever people at work. Okay. Now we're not done. We're not done. By no means are we done. All right? Because now what I want you to do is I want you to work with a diprotic acid. I'm going to give you a diprotic acid. Okay. So you're going to have to work with the ionization equation of sulfuric acid. Okay. So this, by the way, you will not be asked to prove this. I'm just showing you why the pH of a neutral solution is 7. Okay. Now, okay, this I'm going to give you for homework. Okay, but what I want to do now is I want to give you a problem that I want you to do now. We've got 15 minutes and we're going to complete this before you go. Okay, so here's example 2. A 0.5 mole H2SO4 solution, okay, has a pH of 0.5 mole per cubic decimeter the cubic decimeter solution of H2SO4 has a pH of what?
So that's moles, not concentration.
This is concentration.
Okay, so
No, that is concentration. So in essence, what I'm telling you is I'm telling you that the concentration of H2SO4 is 0.5 mole per cubic decimeter Okay, now I want you to work out the pH. This is not the total problem, okay? We're gonna do a reverse problem before you go. This shouldn't take you too long. You need the first step. Step number 1 is the ionization equation of H2SO4 with water. And I will tell you that we can assume full ionization, all right? You need to have this. Then step number 2, you need to work with the molar ratio so that you can get the hydronium ion concentration. And step number 3, is you're going to work with the pH is equal to the negative logarithm of the hydronium ion concentration. Yeah, this should go quite quickly. We've done this in detail, right? You don't have to do the successive ionizations. We can see it's diprotic. So how many protons is going to donate? It's going to donate 2 hydrogen ions, 2 protons. Eh? And you must balance it. Eh? You must balance it. We're going to need 2 water molecules. So H2SO4 donates 2 protons, we know in 2 successive steps. So you're going to need 2 water molecules, produces 2 hydronium ions. Can you see the molar ratio? Excuse me. For every 1 H2SO4, 1 mole of H2SO4, how many moles of H3O plus do you produce? 2 moles. So this is going to be 2 times the concentration of H2SO4. If 0.5 moles per cubic decimeter solution of H2SO4 ionizes, every 1 mole of H2SO4 is going to produce 2 moles of H3O plus. So 0.5, all right, so if we look at this now, oops, my apologies, this is going to be 2 times 0.5, which is going to give us 1 mole per cubic decimeter cubed. Now, if you take this now and you go, okay, so the pH equals the negative log of 1. Now, please don't use your calculator yet. What exponent must I raise 10 to in order to get 1? 0. Wow. This is a mean acidic solution. If this thing's got a pH of 0, you don't want to be anywhere near it.
What is it?
So,
Okay, it's like pH 0 is insane.
So what will be able to like contain that?
Well, you can use plastic.
Really?
Yeah.
Really? It's just like some metal and like to your skin when it's corrosive.
Okay, now, ladies and gentlemen, all right, I am going to give you guys some exercise, some practice. But what I want to do, I want to do something that is going to seem strange. Okay, this is example 3. I'm going to do something strange. Okay. I am going to give you the following, okay? A 0.1 mole, right? Calcium hydroxide solution. Okay, I'm giving you that. Okay, calculate the pH. Now, I'm not going to expect you to do this on your own. I'm going to do it with you. And then I will give you exercises to do. And then what I will do is I will then put out the solutions, right? Next week, you guys will start exams when? Thursday. Now, I think there's still workshops on Monday and Tuesday, so I'll have to do a recording. I will do a recorded workshop, okay? You don't have to come in. I will do a recorded workshop, okay? So, calculate the pH. So, first things first. Okay. What do you think the first step is? What did we do with acids? Ionization equation. So now we're going to work with the dissociation equation. Because remember, alkalis are ionic, they don't ionize, they dissociate. So this is going to be CaOH2 and calcium hydroxide, group 2 alkali. You can assume it's a strong alkali. We will only give you strong bases, strong alkalis. This is going to dissociate in water. It's going to produce Ca+2 plus 2 OH minus. Because it's strong, we can assume full dissociation. It's an assumption. It's not 100% full, but with strong on school level, when we don't work with Kas and Kb values, we assume strong is full ionization. So, step number 2 is we work with the molar ratio. But now what we say is the concentration of the hydroxide ion is going to be double the concentration of the CaOH2 solution. We were given the concentration of the calcium hydroxide solution. This is going to be double. So the hydroxide concentration is going to be 2 times 0.1 mole per cubic decimeter cubed. So therefore, the hydroxide solution's concentration is 0.2 moles per cubic decimeter cubed. All right, now, what have you been asked for? You've been asked for the pH. But the pH is the negative logarithm of the hydronium ion concentration. So how do you switch from hydroxide ion concentration to hydronium ion concentration? You use the Kw formula. So what you do now, step number 3, is you do the ion switch. And the way you do the ion switch is you use Kw is the concentration of the hydronium ions multiplied by the concentration of the hydroxide ions, which equals 10 to the negative 14 at 25 degrees Celsius. Next year, when you do chemical equilibrium, you will learn that the equilibrium constant is dependent on temperature. If you change the temperature, you change the K value. Okay. The K value, the Ke or Kc, which we call the equilibrium constant, is a measure of how far an equilibrium is shifted to the right or to the left. We'll do that next year. So now what we do is we say, okay, this was given to us. We have this, so we can say the hydronium ion concentration multiplied by the hydroxide ion concentration, 0.2, equals 10 to the negative 14. We divide both sides by 0.2. So this is going to be 10 to the negative 14 divided by 0.2. And that is going to give us, I think it's 5, eh? 1/5. It's 5 times 10 to the negative 14, correct? Yeah, I think this time of the day, I'm not going to rely too much on my mathematical skills. It is 5 times 10 to the negative 14. So the hydronium ion concentration is going to be 5 times 10 to the negative 14 mole per cubic decimeter. Almost done. I said you'll be done by 4 o'clock. And then step number 4 is the pH is equal to the negative logarithm of the hydronium ion concentration. So your pH is going to be the negative log of 5 times 10 to the negative 14. And when we log this, we get a pH of 13,301. But hey, that's a basic solution because the pH is close to 14. This is strongly alkaline. Okay, so now, ladies and gentlemen, I'm going to give you some practice. I don't expect you to have mastered this in one sitting. All right, I will give you the following exercises. Let me just show you here quickly. Before you go, I'm going to give you this one. Examples on calculations of the pH of acids. And then I'm going to give you this one, the calculation of pH of a base. So I will give you these these 4 problems to do, and then I will go through the solutions. And then next week I will do a online recorded lesson. I'll put it on YouTube, and then you guys can use it. And the pH is in preparation for your prac exam. Because your prac exam is titrations. If my memory serves me correctly, there are pH calculations in your titration program. Have a wonderful day, ladies and gents. Cheerio. I'll be